One of the biggest misconceptions of modern physics is that phenomena like length contraction and clock dilation don't have physical causes, but rather are merely consequences of the frame invariant behavior of light. That is, consequences of a unique Minkowskian geometry that is presumed to a priori structure our reality. Yet one can easily demonstrate the falsehood of this viewpoint simply by adopting an anisotropic light model, which reproduces all the same mathematical predictions as special relativity without invoking either invariant light or space-time geometry. Since phenomena such as length contraction still occur in these anisotropic models, it logically follows that invariant light cannot be responsible for them, and moreover that such phenomena must be physical in nature. But even more awkward for the modern physicist is the fact that a mechanism for physical length contraction has been implicit within the mathematics of classical electromagnetism for well over 130 years, and yet somehow has managed to go almost completely unnoticed. This is even despite the number of physicists, including George FitzGerald, Oliver Heaviside, Oliver Lodge, Joseph Larmor, and Hendrik Lorentz, who, before the turn of the 20th century, had all more or less hypothesized its cause. Indeed, if one accepts the notion that forces are communicated by waves, then it's a fairly straightforward matter to demonstrate just why any body must suffer a material deformation in the direction of its motion. This is Dialect with the physical origins of length contraction. In an 1889 letter to the journal Science, the Irish physicist George Francis FitzGerald, puzzled by the recent results of the Michelson-Morley experiment, made a daring but dashing leap of intuition. The only hypothesis, he wrote, that could reconcile Michelson and Morley's failure to detect the motion of the Earth with respect to the ether was that the length of material bodies changes according as they are moving through the ether or across it, by an amount depending on the square of the ratio of their velocity to that of light. Now, the Michelson-Morley experiment had essentially consisted of a light signal being sent along two perpendicular but equidistant arms of an apparatus, and then being reflected by mirrors back down to a common center. Over repeated trials, it was found that, regardless of the orientation or state of motion of this apparatus, these light signals always returned to the center at the exact same time. This result, the null result, was problematic because, if the apparatus was in motion with respect to some hypothesized ether, and light in turn could only travel at a constant speed through that ether, then the signal sent along the arm parallel to the direction of motion would have a farther path length to travel than the signal sent along the perpendicular arm, and hence should return after its companion. But this was never observed. The signals always returned concurrently. Thinking this over, FitzGerald came to a significant conclusion. If the length of the arm parallel to the motion of the apparatus were somehow contracted in consequence of that motion, then the light signals would always travel the same path lengths through the ether and hence return at the same time. The Dutch physicist Hendrik Lorentz would come to the same conclusion in 1892, stipulating that the length of the Michelson apparatus, as well as that of the length of any material object, must undergo a contraction by a factor of the square root of 1 minus v over c squared, or 1 over gamma, in order for that object's motion through the ether to be masked. And by 1904, he had formalized this mathematically within the famous transformation laws that bear his name. But to some individuals, the idea that all material bodies must somehow contract in the same particular manner was too far-fetched. Indeed, in 1908, Albert Einstein decried the idea as implausible and ad hoc, arguing that length contraction instead followed as an ineluctable consequence of his conception of the relativity of simultaneity. However, as we examined in a prior video, Einstein failed to grasp that the relativity of simultaneity is purely a measurement convention, and hence cannot be responsible for any phenomena whatsoever. But more so than this, Einstein neglected the fact that a highly plausible explanation for length contraction had already been put forth. For after proposing the phenomenon in his 1889 letter, FitzGerald had immediately thereafter offered up a hypothesis as to its cause, writing that, because the strength of electric fields were altered by motion, it was not, therefore, an improbable supposition that the molecular forces are affected by the motion, and that the size of a body alters consequently. Similarly, in his seminal work, The Theory of Electrons, Hendrik Lorentz wrote, "We can understand the possibility of the assumed change of dimensions if we keep in mind that the form of a solid body depends on the forces between its molecules, and that, in all probability, these forces are propagated by the intervening ether." Now, while modern physics has essentially swapped the word ether for vacuum, this idea that forces themselves must propagate is still upheld by the principle that information can only travel at a finite speed. And indeed, modern theories trade in the idea of force carriers, or bosons, packets of momentum that propagate as waves. So what really happens then if we take such ideas seriously? The first half of this picture, how and why molecular forces are affected by motion, we covered in detail in a prior video. The idea is very straightforward. At any given location in an electromagnetic field, you have something called an electromagnetic scalar potential and an electromagnetic vector potential. Together, these two potentials completely determine the behavior of the electromagnetic force there, in accordance with these equations. The specifics of these equations don't really matter for our purposes. All we need to understand is that once we possess information about the potentials, we then know everything about the electromagnetic forces there. Now here, things get interesting. The four famous equations of Maxwell's theory can be expressed in terms of these potentials through just two equations, which turn out to be, well, straight-up wave equations. Physically, this means we can treat the potentials themselves as emanating in a wave-like manner from any electromagnetic source, in the form of disturbances that travel through space at the speed of light, c, and whose magnitude falls off as 1/r. Although the stimulation of these disturbances is truthfully continuous, the picture here will be easier to understand if we depict it with discrete wavefronts. Now, first, let's consider our source to be stationary. Then the potential wavefront passing through any point always has the same magnitude, kq/r. And the result is a static electric field. Next, however, consider that the source is not stationary, but rather moving with uniform velocity. Then in this case, the potential wavefronts are redistributed in accordance with a classical Doppler shift. For any distance r out on the right, a single wavefront has farther to travel to reach its destination as compared to that of a wavefront at rest. And the potential there is consequently decreased. However, the wavefronts are stacked closer together, so that the density of potential through that region, and hence the total potential itself, is actually increased. The net result, so long as the motion of the source is uniform, is that these two effects exactly balance one another out, such that the total potential at a distance r out remains precisely the same as for that of a charge at rest. Similarly, to the left, wavefronts have a shorter distance to travel to reach their destination as compared to ones at rest, and thereby experience less falloff. So potential is increased in those locations. But the wavefront density there is simultaneously decreased, and the two effects again balance out. In the transverse direction, meanwhile, no such symmetry exists, and the potential there ends up being increased by a factor of gamma. We thus arrive at pancaked or ellipsoidal potential fields that are entrained by uniformly moving charges, both of the scalar and vector kind. To determine the electric field that results from these potentials, we next apply this equation. The first term, minus the gradient of the scalar potential, implies that the electric field mimics the shape of the pancaked potential field. That is, along the longitudinal direction, the electric field is unchanged from that of a field at rest. But in the transverse direction, it's strengthened by a factor of gamma. This second term, however, minus dA dt, means we have to subtract away from that field an amount proportional to the rate at which the vector potential changes over time there. Because A reaches its maximum value whenever it coincides with the transverse axis of the charge, its derivative there, that is, its derivative whenever the charge passes it by, is momentarily zero. And so this second term ends up eating away at the longitudinal components of the field, such that the field is reoriented towards the instantaneous position of the charge. The end result is that the electric field of a uniformly moving charge is strengthened by a factor of gamma in the transverse direction, but weakened by a factor of gamma squared in the longitudinal direction. The general angle formula for the field, meanwhile, is given by this expression. And as it turns out, this expression is all you need to explain the phenomenon of length contraction. Why? Well, because, just as FitzGerald and Lorentz hypothesized, once you've shown that electromagnetic fields become altered by motion, it follows that molecular forces and bonds must also be altered. But of course, given that bond structures differ widely from one material to the next, how might we demonstrate that this alteration should occur in the same manner for any given material whatsoever? Well, whatever our knowledge about the inner bond structure of a material or body may be, there is always one thing we can say about it for certain, which is, in order for a body to be stable, its constituent components must be in equilibrium with one another. That is, for any given constituent component within that body, the electromagnetic forces acting on it must sum to zero. And this in turn must be true whether or not the given material is at rest or in uniform motion. Now, both electric and magnetic forces may act on a charge, but the magnetic field of a moving charge is proportional to its electric field. Meaning, for any ensemble of moving charges, wherever the electric field sums to zero, so too must the magnetic field. We can express our equilibrium condition most precisely then by stating that the sum of the electric field acting on any charged constituent within a moving or at-rest body must be zero. Now, this next part is very important. Taking our body to be at rest, If we decompose the electric field acting on any stable charged constituent into 4 equal and opposite components, then this decomposition is physically equivalent to that charge being at the center of a diamond-style arrangement of opposite charges of a slightly greater magnitude. That is, because forces superimpose, then the state of equilibrium of a constituent charge in any body can always be treated as though that charge were at the center of a diamond-style arrangement of charges, regardless of whatever the true configuration of charges might be. This diamond-style arrangement can thus be stipulated to physically represent the infinitesimal length elements of a body, dx and dy. Indeed, so long as this system is at rest, the electric field components acting upon each of the 5 charges sum to 0, and the configuration is in equilibrium. Once in motion, however, the fields of the charges change shape and magnitude, and consequently their components no longer sum to 0 at the respective charge locations. The system, therefore, can no longer be said to be in equilibrium, and hence no longer be said to represent the same material or body which it represented at rest. To resolve this, we need to find a new configuration for our moving charges then, such that their altered fields once again vanish at each charge location. Assuming our arrangement deforms symmetrically, we can take the equation for the electric field of a uniformly moving charge determined earlier, calculate the total field component acting on each charge due to every other charge, and then determine what must be the relation between the new longitudinal and transverse lengths dx prime and dy prime, such that those components all vanish. After churning through a bunch of math, lo and behold, that relation turns out to be the following: dy prime over dx prime equals gamma. Now, strictly speaking, this means the configuration of charges could take on a contracted shape of any scale. However, it shouldn't be too hard to convince yourself that the arrangement which minimizes the work done on the configuration is that wherein dy prime equals dy, and hence where dx prime equals 1 over gamma dx, or the square root of 1 minus v squared over c squared times dx. Again, since any configuration of stable constituent charges can be modeled via such an arrangement, this implies that in order to remain in equilibrium, any moving solid body must experience a contraction relative to its rest state. And so, 137 years after its first suggestion, the daring hypothesis of FitzGerald is finally brought home. Length contraction, far from being an ad hoc conjecture, turns out to be a physical reality directly implicit within the wave dynamics of classical electromagnetism. Meaning, we're finally in a position to show that it is Einstein's axioms which are in truth the ad hoc ones, and that the theory of special relativity can be fully derived without any reference to them whatsoever. But that's for future videos. So until then, for more details, fuller derivations of the subjects in this video, and behind-the-scenes glimpses into our animation and video creation processes, come on over to our Patreon page. This has been Dialect. Thanks for watching.